Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we got no problems because we are continuing our discussion about electricity. Electricity is cool, and I'm going to teach to you one of, I think, the most difficult concepts, like in all of electricitydom. It is something called electric. Now, electric potential is electric potential energy. You remember potential energy. Now, we measure electric potential in something called a volt. Now, surely you've heard of a volt. You buy batteries that are 9 volt or 1.5 volt batteries. So you've seen this term a bazillion times. But what does it mean? It has to do with the potential energy of something. Electric potential. But let's talk about this from the physics stuff we've learned about before. When we've talked about potential energy, that has to do with a term we're familiar with called work. If you recall, work is force times distance, right? Work is force times distance. Now, when we put this in electric terms, all right, we know what force is, right? We've got electrical force, right? Actually, let's do this. We knew that electrical force is equal to Q, right? The charge times the electric field. We learned that in a previous video. So the work would be equal to F E-D, fed, right? Or actually it's typically written, and so this is also, by the way, the work could be equal to the potential energy. So the actual sort of official equation is that the potential energy is equal to QED. This is the electrical field. Now, we calculated that in the previous video. Or another way to say this, which leads us to probably the most important definition of our conversation, is that the volt, or the change in V, now we're going to use the term V for volt, is equal to the change in potential energy, that's this number, divided by the charge. And the units on this is something called a joule, potential energy. All right, remember, potential energy is energy. Energy is energy, energy. That's a joule per coulomb. So if I've got a coulomb of electrons, right, remember, coulombs are the charges of electrons. This is the energy per joule of electron. Now, you're probably going, I'm still lost, Mr. Bergmann. I don't understand what you're talking about. Let's talk about potential energy from an electron perspective. I mean, take a look at the picture of the gal in the picture, right? She's got a positive and a negative charge, and think of them like a spring. And that spring is causing them to attract. And so for her to separate them, to squish them apart, that's going to take some work, right? Right? And by the way, the reason we're getting to all this is that this work, we can do things with electricity. This is what allows us to power up our lights and power up our cell phones and all these kinds of things. Conversely, in this picture, we got the dude with the 2 positive charges, and they want to repel, so he has to push them together, and that's going to require some work, right? Now, if you can hold those 2 things together, or hold the opposite ones apart, what you can do is when you release them, as they move, either away or towards each other, then they can do some work, which could do things for your devices. So let's come back to this concept. What the heck is a volt? This is an important understanding. It's the amount of joules you can have in 1 coulomb. So if I got a 9 volt battery, that's a pretty high voltage of a battery, I've got 9 joules for every coulomb of electrons that I have. It's almost like the density of energy that's inside of the battery, or it could be a device or whatever it might be, right? So let's do this example right here, right? Find the charge and electric potential energy as a charge of 2.2 10 to the minus 6 coulombs moves from point A to point B, right? The charge, that's electrons moving from point A to point B, given the change is 24 volts. Now you recall, again, the potential energy is equal to Q delta V. Now this is written a little differently than I did before, but basically that's another way to write it, all right? And we're simply going to multiply the numbers, right? 2.2 times 10 to the minus 6 coulombs times the voltage, which was 24. Let's write it out, 24 joules per coulomb. The coulombs cancel. Take these numbers, multiply them together, and you get 5.28 times 10 to the minus 5 joules. So that's how much energy you can get out of a 24 volt battery that has this many coulombs traveling from point A to point B. So let's see if we can understand the difference. It's quite confusing between electric fields and electric potential. So an electric field, that's the E. The units on that, if you will, is a Newton per coulomb. And the unit on, that's just the units. And for volt, or electric potential, that's a joules per coulomb. Now Newton is force, joules is energy. So it's force per coulomb, joules per coulomb, right? So these are the units. So to think about the units, maybe a better way to look at it is to look at these images, this ski slopes. The electric field is like the slope of the line. It's how much force you can get out for every mole of electrons. Okay, and so in picture number 1, you have a steeper slope than picture number 2, right? But now, so that means that the electric field is the same, but the voltage is the same because the voltage is just how tall the hill is. It's the total amount, if you will, of potential energy that you can get out of the system. Conversely, if we change the height of the hills, picture number 2 here, if you will, and they both have the same slope, the first one has a small electric field, and the second one has they both have the same electric field, but the electric potential changes because they have different heights. So maybe that analogy makes sense when we think of it from a gravitational perspective, as we're thinking through the difference between both electric field and electric potential. This is the amount of energy you can get out of something, and maybe this is how fast you can get it out. Maybe that's a better way to think of it. So maybe to help illustrate and kind of figure this all out, let's do this problem right here. Right, the electrons in a TV picture tube are accelerated from rest through a potential difference of 25 kilovolts. Okay, what's the speed of the electrons after they're accelerated by this potential? Speed. Now we're going to use an equation. Now that all right, potential. Let's think this whole thing here through. Let me think this through. Now to solve this problem, we're actually using elements of stuff we learned in previous physics units and videos, right? Potential energy, right, in the context of electricity is Q times the change in volts, right? So that's energy, but now we're talking about velocity because the potential energy is being converted to kinetic energy. We can set that equal to 1/2 mv squared. And if you look at the question, right, it's asking you to solve for the velocity. Now we know the Q, that's the charge of the electron, right? And we know that number to be 1.6 times 10 to the minus 19th, right? We know that. The V, the change in the voltage, they gave that to us as 25 kilovolts. So if you think about that, that's 25,000 volts equals 1/2 times m. Now this is the mass of an electron. So when you look it all up, I didn't write it out there, probably shouldn't, probably 9.11 times 10 to the minus 31 kilograms times V squared. Now we set this all up, I get my calculator out, and that gives you, and then I'll multiply these together. That's a V squared, so I'll divide both sides by this term on this. And that equals V squared, so I'm going to take the square root of both sides. And I get 9.9 times 10 to the 7th meters per second. By the way, the speed of light is 3 times 10 to the 8th meters per second, so relatively close to this one. But that's how you solve these problems. So you're basically setting the potential energy equal to 1/2 mv squared and solving for V. So yeah, I mean, electric potential can help us solve things because electricity can do things. That's the whole big point that we're leading into so that we can power our devices. Houston, we don't have a problem. We're going to see you in class.